So let me start by repeating some of what I said last time. So actually, for once I made reasonable notes, so let me follow them. So given a topological space, let me call it X. We introduced base topological space. We introduced the path vibration. Px over X, and showed that the notation might be slightly different, but there is a natural map natural equivalence from the loop space, the base loop space of X, to the space of fiber-wise maps over X of path space. And just to remind you what this was, is that, if here's my base point, here's a path, the action, and here's a loop, the action was by concatenation. Okay, if you take this loop and concatenate it with this path, this endpoint doesn't change, so it's a map from the path space to itself that preserves the projection. So now, if X is a manifold, and f from X to R is a Morse-Smale function, then what I started introducing last time is some kind of, what I introduced last time is a Morse theoretic model for not this map space, but the corresponding thing in spectra. So, okay, so how did I do this? So then we denoted by Txy. So basically T means trajectory, the space of the moduli space of gradient trajectories from critical point X to a critical point Y. Okay? And something I did not do last time is I would like to introduce some notation. So we have an evaluation map from Txy to something which I'll write paths from X to Y on X. So this is paths, well, from X to Y. And my convention basically is that if X is the base point, then if one of these is the base point, then I just entirely omit it. Okay? So it's compatible with the previous convention. So before we wrote P sub Y, for example, for paths from the base point to Y. Okay, so we have an evaluation map from here to here, which is just saying, well, these are actual gradient trajectories. So now there's two essential points. I didn't actually talk about it. I decided not to talk about it. It's not worth it. So we're just going to talk the gradient trajectories. Yes, if you try to do this correctly, you have to take some compactification, but we don't worry about it. So there's two essential points. First is that we have a concatenation map. So here we were concatenating at this end. This was the base point and this was x. Okay, we were concatenating this end. But you can also concatenate at the other end. Map. P, you could do this in general, but anyway, x cross p x y, p y x. Okay, this is just concatenate along x, or attach. Oh, there's too many symbols that kind of look like, which is concatenate at x. 2. Okay, and this is what I talked about last time in terms of these manifolds T of x, y have stably trivial tangent bundle. And the proof of that is, I didn't do it, and in fact, it would take us quite a while to prove about it. Anyway, I didn't do it, but what I want to do is I want to say the consequence of this is that if, in this simplest case, which is if Txy is a closed manifold, then there exists canonical up to stable homotopy map from a sphere, it's closed manifold of dimension d, from a sphere of dimension d plus k to sphere of dimension k smashed with Txy. Okay, and the reason is that this thing here is the same as the Thom space of trivial vector bundle on Txy, and the condition that the manifolds have stably trivial tangent bundle tells you that if you were to embed Txy inside Sd plus k, if you were to embed it, then and the codimension is large enough, then the normal bundle is trivial, and so this is some kind of collapse map where you collapse everything outside the neighborhood. So this is sometimes called Thom collapse map. Of an embedding of this inside there, and this construction, this correspondence between manifold with stably trivial tangent bundle and maps, some kind of maps from spheres, is a version of what's called Pontryagin-Thom theory. Yeah, I can. Let me draw a picture. So the picture you should have in mind is, so here's the kind of the big ambient space. Here's this manifold embedded inside this ambient space, okay? And now take a tubular neighborhood. So this tubular neighborhood, by these assumptions of stable triviality, by stable triviality and by kind of raising the dimension a little bit, you can assume that this stable tubular neighborhood is trivial. So the fiber here is just identified with Sk. Okay? It's a neighborhood which is basically like a Sk, fiber is Rk, minus 1, fine. Rk. Okay? That's the trivial neighborhood. And now you just collapse everything. I apologize. Let's make it dk, which is the disk. Okay, let's make it a tubular neighborhood with closed tubular neighborhood. Okay, so now you collapse the boundary of the tubular neighborhood to get, well, to get the Thom space. But because it's trivial, because the tubular neighborhood is trivial, this Thom space is exactly what I wrote, SK smashed with TXY. As in the previous lectures, I don't keep track of base points. Like, there should be like an extra base point here. But now, if you've collapsed the boundary, you can also collapse everything outside the boundary to that same point, to that same boundary point. So the map we get, map from S D plus K to here is just collapsing the complement of the tubular neighborhood to kind of the boundary, image of the boundary, to the base point, let me say it like that, base point of the Thom space. Okay, does that help? Okay, so these are the two essential ingredients. Sorry, small. Oh, interesting. Sorry. Okay. And now what I want to do is I want to explain how they come together to give us the analog of the Morse differential that we may or may not know from Morse theory. I'd like non-colored chalk. I don't have enough white chalk. I'm running out of white chalk, so okay, I guess there's some more pieces left. Good. So how does that happen? So this is the thing that last time was the very end, and I kind of botched it. So let me try to get it right. So let's say we are given phi, which is map from P x, Px. Okay, so let me again repeat. Our goal is to build some kind of Morse model of this space. Okay, it won't be of this space. You should imagine like of its homology. But in the way, the language that I decided to use is of its suspension spectrum. But anyway, what would a Morse model look like? A Morse model should be built from a union over the critical points, x critical point, of the maps of the fibers of this. Pxx, Px. Okay? So you just look at paths from the base point to x. You take the space of all maps from those paths to themselves, and somehow, if you glue them together correctly, you should recover this space. Okay? That's the basic idea. But we're not going to recover the space. We only recover it after linearization. Nonetheless, this is the right thing to do. Let's just start with such a map. So what I want to do is I want to assign to this, so x is a critical point, and we're in this setting where we are looking at flow lines to y. So then let's consider following map. So you go SD plus K of P, Y, X. Okay? So what is this? This is I take this space and I suspend it D plus K times, or I take the smash. I suspend this D plus K times. Now, I apply this map here. Okay? Very reasonable. That's why I introduced that. Then you use the fact that the space of gradient trajectories act. Gives me a space of gives me paths from x to y. So let's just do that. Okay? But I want to do it the other way. Sorry. So, P of yx. Okay? So now all I'm doing here is I'm taking the space of gradient trajectories and I'm embedding it inside the space of paths. That's what I was saying right there. Except I'm putting it in the other order so to make so that, anyway, I can concatenate in either order. Okay. And now, instead of just doing this, I also want to take a diagonal map. So this is diagonal plus the kind of embedding. Okay, so now you concatenate here. So this goes to sk smash txy smash px. Okay, you just concatenate. And now you concatenate again. I'm just going to do this. Okay. So if I take a trajectory from x to y and a path from the base point to x, I can concatenate that to get a path from the base point to y. So then I have a map here. Oh, sorry, missed one thing. So I missed one thing, sorry. Before we do that, say we have this phi, which is a map from px to itself. Now I apply phi. And finally, I can go there. Okay? So this is, again, concatenate. So I want to ask, is there any of these steps that's not clear? So this is the Tom map. This is maybe the one that I haven't talked about so much because it's just the identity. Instead of just saying, all I'm doing here, instead of just taking the inclusion of the Tom map of the gradient of the space of flow lines inside the space of paths, I say, well, I take that inclusion in this factor and I take the identity on this factor. Why do I do that? I do that because at the end I need to concatenate again, and if I don't do that, I don't have this factor to use anymore. Okay? This is just some kind of technicality to because last time when we talked about this, we saw that you have to concatenate once and then concatenate again. So we need to do it twice, and this makes sure that you can do it twice. Okay? Then you concatenate to land in space of paths which end at x. Then you apply your map, phi, and then you concatenate again to land there. So this gives a map from maps px, x, pxx to maps from the suspension. So let me write it like this: d plus k p y x sigma k p. This one? This is the composite of all these things. Composite. I just want to highlight it because that's what we're going to use here. Sigma k of p y x. Okay. So if you do Morse theory, if I said we want to do Morse theory, what you would say is you'd map this thing to the analogous thing for y, but it does not make sense. That's not at the level of topological spaces, that's not what you get. You get it up to some suspensions. Okay. So if you linearize this, and by linearize this, now you can do whatever you want. If you want to take homology theory, you can just take homology theory. I will take spectra. You get a map from from the function spectrum of the suspension spectrum of px, x, p, x. Oops, no, this is probably the suspension spectrum. 2. Now what happens is, when you pass to the suspension spectrum, this k and this k, they basically cancel out. It doesn't matter anymore, because when we defined these guys, we said they are some kind of limits as something goes to infinity, blah, 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 where you suspend the two things by the same amount. But these things are not suspended by the same amount. This one is suspended by d more than this one. Actually, sigma minus d. F sigma infinity pyx infinity pyx. Okay? So these two ingredients, okay, they combine together to give this map. If you really want to prove that it gives you this map, what you have to do is you have to show that this here, I really just said maps from this guy to this guy. You have to say, well, what happens if I suspend this once and I suspend this once? Then this procedure should somehow be compatible with suspension. But that's just bookkeeping. There's no new idea when you prove that. This is the only idea you need. So you want to interpret this as a map of degree d from minus d from the fiber of the Morse complex, or the summand of the Morse complex at x to the summand at y. Okay. And this may be slightly unfamiliar, because usually in Morse theory you only have degree 1 maps. Okay? Or minus 1s, because I'm doing homology, degree minus 1 maps. But that's because when you're doing Morse theory, usually reasonable in our setting, because unlike classical Morse theory, our summands are not supported in a single degree. Again, I'm talking about spectra, but you could just imagine that I'm instead working with chain complexes. Usually in Morse theory, you're going to say, well, I'm going to take a direct sum of a copy of the integer, for each x critical point, and I'm maybe going to shift this by some kind of degree, shifted by the Morse index. I'm not going to write it. I'm just going to do shift by Morse index. But now the way you want to imagine each of these copies of z is that, so there is some kind of minus 1, minus 2, minus 1, 0, 1, 2. And so if you look at the specific critical points for x, it's going to be 0, 0, 0, and then it's going to be maybe like a copy of z here, and then 0, blah, blah, blah. Okay? And then for a y, okay, you're going to have the same thing, but maybe it's shifted by 1. Okay? So then you see some kind of map here, and everything makes you happy. But imagine that instead of having these z's, you had something which were much larger, which were some kind of supported in more degrees than that. Yes?
The analogous thing that people might be familiar with, they try to compute Morse homology over fibration by...
Yes, thank you. Thank you. Yes. I will say that. Yes. I'm doing something similar. Yes. So you can, thank you. So as Janko points out, so in classical Morse theory, you can implement the Serre spectral sequence by replacing this copy of Z for a fibration, anyway, by something like the cohomology of the fiber. Okay. And then instead of just this copy of Z here, you see like H0 of the fiber, H1 of the fiber, H lower star because we're doing homology, H1 of the fiber, and so on and so forth. And now what happens is, if you shift things, if you shift things by one, didn't exactly put myself in a good position here. If you shift things by one here, let's say H0, H1, H2, okay? Then, you have this map here. You could have a map here, and this map is essentially some kind of differential. But if you shift by two, you can also have a map like this, okay? So that's the phenomenon that's happening. Once you are in a situation where your pieces of the Morse complex are not just supported in one degree, then you cannot expect the maps to just come from the rigid flow lines. You really need all the moduli spaces. And what I'm doing here is explaining some kind of universal case where you take the universal fibration over X, which is the path fibration, and you try to recover its stable homotopy type. And you do it by taking all the flow lines and seeing how the flow lines give you maps between the function spectra of the endomorphisms of the fibers. Okay, so just to be clear, this actually does not conclude the construction. You still have to do some work. Yes? These maps here are, exactly the family. Yeah, you take. Okay, so you can interpret what he did as some kind. Yeah, and I won't say anything, but it's analogous. It may even be exactly the same. So what I want to say is that we're not quite done yet, unlike that case. In this case, there's more work to be done, and so what I did not explain how to deal with this Txy when it is not closed, when has boundary, when this moduli space has boundary. Okay, and to be completely honest, when you do it, it is just a matter of combinatorics. If you try to do the combinatorics by hand, it gets nightmarishly awful, but this was worked out by Cohen, Jones, and Siegel. They worked out some framework for doing this kind of thing, for dealing with manifolds, for flow trajectories that have boundaries, and then you can just implement it in this setting. Okay, that was the end of the review. So now I have 1 hour to talk about the next case. So the theme, the goal of this series of lectures is to explain what should happen if you like to do the same thing with Floer theory. What about Floer case, Floer theory? And in this, for me, what I mean by Floer theory, I mean Lagrangian Floer theory. We haven't talked much about it, but it, somehow, yeah. Floer theory of a pair L inside M, where this is symplectic, and this is Lagrangian. And what I've been trying to indicate is that the correct space to look at in that situation is not the space of loops, but this space of disks. So replace omega 2, omega by omega 2 ml based disks. So the first thing that I want to do is I want to recall with a little bit more notation the analog, oh, I erased it, the analog of this description of the space of base loops as obtained from fiberwise maps of the space of paths. So what's the analog of that? Well, I'll just skip directly to the Morse theory part. So now this is some notation that I didn't introduce last time. Oops. So let me, for each x in L, let S x, what's my notation? ML denote the space of maps from a disk. Okay, this S is for square. Well, let's still write disk. To M. Sorry, I'm getting some. Let's just move it a little bit, see what happens. To M that look like this, with the following boundary conditions. So I'm going to draw now something. So we take disks, and instead of thinking of disks as circles, we think of them as squares. Okay? I want this corner here to go to the base point. Remember here, I have a base point in L fixed. Okay, I want that corner to go to the base point. I want this entire edge here, this entire edge to go to X. Okay, I want this to go to L. I want this to go to L, and I want this to go to M. Okay, and this inside goes to M. Okay, so this is kind of a strange space. And last time when I was describing the analog of that fibration for omega 2, I said take some space and then replace it by a fibration. Take some map and replace it by a fibration. This is a replacement of some map by a fibration. You'll see in a second what I mean by that. So this evaluates from S, X, M, L to the space of paths. So this is the space of paths from the base point to L in M. I'll write that again. Crossed over L with the space of paths that end at X and are free, and this is really troubling. So let me just do it. Let me not do that. Let me just do PX ML. Okay, so it has an evaluation map to there. And what's this evaluation map? It's just this end here. Okay, given by the outer edge. Okay, but it also has an evaluation map to the space of paths along L from the base point to X, given by the orange edge. Okay? So claim this is a fibration and this is a homotopy equivalence. So this is fibration and this is a homotopy equivalence. Okay? Is that okay? This is typical of these kind of things. The reason this is a fibration is that if you give me the yellow one here, okay, and you move it a little bit, you can just move the values along the square to kind of, along with the values along the boundary. The reason this orange one is a homotopy equivalence is because I've put no condition right here. There's no condition right there. So in particular, you can just take this thing take this yellow one and create a new square by just kind of, going like this, using the values inside. Okay? So homotopically, there is no data in this yellow stuff. You can just push it inside and get the value of the orange one. The value of the orange one determines, up to contractible choice, the value along the yellow one. What's not literally true?
So you have the condition that you were on L.
I mean, okay, picture is not literally true. Here's now a picture that's literally true. Thank you. Okay? Okay. So you'll see there's simpler models for this, for making a fibration here, but this one is going to be nicer for what we'll do later. Okay. So what do I want to say about this? What I want to say is that we want to build a Morse model for loop to ML from the union over all x over all critical points of a Morse functions of the space maps from this square to itself okay? And what I want to say is over this. But I will write it. If you try to be extremely careful, you'll realize you don't want it to be over the identity of that. You want it to be somehow over some kind of contractible choice of some self-maps, but I don't want to be precise. So let's just do over this. Okay? So last time, I tried to explain why, how such a thing is related, is related to the second loop space. Okay, but this time I have even more tools to explain it. So let me take this picture and let me undo the fact that it's a square. Okay, so let's draw the So I claim that this maps naturally to the space of maps over this, from this to this, maps naturally to the second loop space. Okay. Maybe a little bit surprising. So why is that? So what you do is you draw this picture like this. So I have L. Okay. I have my base point. I have the yellow thing along. Oh, this is going to be really hard to draw. There you go. So this is the yellow part. Maybe what I want to do. And of course, there's also this part of the yellow part. Let's ignore it. Let's pretend that that entire part is constant so that I don't have to think about it. And this is the orange part. Okay? And now, let's say that I have a map from this to this over this. Okay? So what does that mean? That means that, we're talking about this guy here. Okay? So I have a map from this to this over this. So that means that associated to every such disk here, I have with one boundary here and another boundary that just kind of moves in space away from L, I get another one. So this is some kind of U, and this is phi of U for phi that lives in the space of maps. Okay? But now the key point is that phi of u, because this is a space of maps over the space of paths, okay, u and phi of u have the same boundary. So you can glue them together. Okay. So glue together, glue phi of u to u along the boundary, the common boundary, and you get a disk. So this is the key idea. And in fact, if you remember the proof that the base loop space has the same homotopy type as the space of fiber-wise maps, we also used that, exactly that point, except we used it with paths instead with one-dimensional thing, instead of doing it with two-dimensional things. Yes?
So then not this mapping space has a map to this space, but to this times this S space.
No.
Because you need it.
Oh, yes, yes, thank you. Yes. Let me see how I want to say this. I take map. Yes, this times S, X, ML. Thanks. If you have this and you have that input, then you do that. Okay. So this is some kind of key point. Okay, but now what do I want to, how do I want to?
Why did the?
Well, if I have a map phi, then I need u in order to apply this to.
Oh, right.
As if I take a phi and a u, then I can take the u and I glue it to the other side of the phi and they go together. Okay. So now, and of course, and you can see that this picture that I drew is not exactly that one. It's just because of this extra edge, and this extra edge adds homotopically doesn't add any extra data. So let me consider something different. Be the space of maps. From a disk. From a disk to M with these boundary conditions.
Map from U to P of U, and that gives us
I'm happy to pause for a second and think through this, but so. So yeah, so this is exactly what we're trying to figure out. I claim that there was a map from this to the space of base disks, but it seems that you have to take the product with this domain. So let's think about it. So if I have instead of saying this maps, so the product of S just 1 second. Yes, S, X, M, L with this space of maps. Product of this domain with the space of maps has a natural map to this second loop space. Are you happy, Yasha? No, still not happy?
Yeah, I think so.
Okay, so so this, now what I mean by this will be the space of maps from a disk to M with boundary conditions like this. Okay? And so you see that there is a natural map. So we have S, X, the earlier guy, ML, cross with S, X, Y, ML, goes to S, Y. Okay, well, how does it go there? It goes by concatenation. Okay? So, what does this tell us? It means that if we have a manifold, let's call it for now R, X, Y, embedded inside S, X, Y, and L. Okay? Then we have one of the two different ingredients that we needed in order to build our desire, in order to that we used in the first part, and we tried to kind of build a complex, kind of by gluing these together. One of the two ingredients for building a complex. So, in fact, we always have such spaces. So what do I mean by that? I mean, without assuming anything about M and L, just assuming that they are manifolds, or any manifold pair M comma L, not symplectic and Lagrangian, we can set T Rxy to be just the space of gradient flow lines. Why is that? Well, this is supposed to be some kind of maps from a square into M with some boundary conditions on L. Okay? But of course, there's an inclusion of flow lines from X to Y inside here, given by just taking the product with a constant map in this direction. No, I said if we have such a thing, then some manifold, don't know how we're going to produce it. Floer theory, but okay. But if we had one, we would be able to use it. Okay, but we'd at least be able to use it in the concatenation side. But I'm trying to say, like, if you're not using Floer theory, if you're just using Morse theory, you already have such a manifold. The space of gradient flow lines from X to Y, or in fact, just the space of maps from an interval to X to Y, maps to this space of squares. How does it map? By taking the constant thing in the M in this direction. So again, this maps into the space of paths from X to Y along L, and then this then maps to the space of squares from X to Y along M and L, and this is just constant in the second factor. So take interval to product with constant map in the M direction. You just don't leave, you don't have to leave L, you just stay along L. I mean, again, clearly, this, inside of this, there's a space of squares such that all the values lie on L, and among those are those which are actually independent of this variable. Great. And so, from this, you can recover the homotopy type, the stable homotopy type of omega 2 and L using Morse theory on L. Good. But now, if we are in the symplectic setting, if M is a symplectic manifold and L is a Lagrangian, then there's other things you could do. In the symplectic setting, let's just take this square to make it more familiar. L, L, M, X, Y, and draw it like this. And maybe draw that like this. Okay. Well, there's a natural candidate is the space of holomorphic disks. With boundary on L, okay, that passes through X and Y. Okay? Well, actually, if you're very careful, you realize that, of course, you could use such a moduli space, but really you should have used first the Morse flow lines and then this moduli space. So typically what is done is that you don't just directly use this moduli space, you use something like more carefully. You want to set this space R X, Y to be something like this. It has in it the gradient flow lines. Okay? And then you take the union of the gradient flow lines with a flow line from X to some holomorphic disk. Ah, this is a bad picture. Usually it's just drawn as a circle. And then followed by a flow line to Y. And it turns out, unfortunately, if you do this, that you have to add more contributions. But the essential thing to think about is just the disk part. And the rest is just kind of how you chose to implement some things. It's not really. So it looks pretty good. So what it looks like is that we have a differential that gives us the second loop space, okay? Always. But in the symplectic world, we have some additional things we can use, which are these space of disks. Okay? And this phenomenon is kind of typical. Sometimes it's called like quantum corrections. But the idea is that Floer theory, and here Floer theory just means holomorphic disks with boundary on L. Deforms the homotopy type stable of this second loop space. Okay. Unfortunately, this statement is not right, and I'm about to explain why it's not. So this is. So now I will add the proviso that allows you to make a correct statement, and the proviso is after twisting. Okay, so why do you have to twist? When I explained how to recover the base loop space from a similar construction using Morse theory, there were two ingredients. One ingredient was this concatenation, the analog of this concatenation, and the other ingredient was the stable triviality of the moduli spaces. And so the problem is the tangent space of the moduli space of disks is not stably trivial in general. Okay. So yesterday there was a lecture describing, yesterday evening we had an evening lecture, which was about linearization of the D-bar operator, and which basically said, well, if you want to understand the tangent space of the moduli space, and what you do is you build some kind of Fredholm problem, like a infinite dimensional, a Banach bundle over the space of maps, and then the Fredholm section, and then the kernel of that Fredholm operator is basically the tangent space of the moduli space. There's no reason for that kernel to be trivial, okay? But yesterday, so one of the points that was discussed yesterday, and yesterday it was stressed for kind of analytic reasons, and today I really want to use it for topological reasons. We saw that there is a Fredholm problem on the space. Let me just be a little bit more precise. So that there is a Banach bundle which maybe called yesterday was called like maybe E over the space of all sufficiently regular maps, maps from D2 to M, or really it's more like D2L, D2S1 to M comma L. Okay. And an operator. So let's say the space, let's call this B, and an operator from basically the tangent space of B to E, which is Fredholm, such that the kernel, or really, I really want to say the index of this operator, which means formally take the kernel minus the co-kernel, is a stable vector bundle on the space of all maps, whose restriction to the tangent space, to the moduli space is the tangent space. It's a long sentence. Next up, this operator, let's call is gives a vector bundle, gives a stable vector bundle nu on omega 2 ml, whose restriction to the moduli space of holomorphic disks is isomorphic to the stable tangent space. Actually, for convenience, it's convenient to, I mean, it doesn't really, not exactly how, anyway, to the stable tangent space. I'll just do it like this. Okay? So that's some input from analysis. So you take this moduli space, not only can you make it a smooth manifold, but in the process of making it a smooth manifold, you have to build something, you can build something global, which doesn't rely on the map being an actual solution to the Cauchy-Riemann equation. And that global thing, it's not quite a vector bundle because generically, well, you know, generically the, excuse me, I shouldn't even say that, because somehow, sometimes this operator has a kernel, sometimes it has a co-kernel, sometimes it jumps. But even the way that it jumps, it's not a problem because you have something, you only care about things stably. Okay? So the output you get is a stable vector bundle on this. Okay? And now comes something, I want to use something from 2 days ago, from Su's evening lectures, which is that this bundle is multiplicative. What that means is we have a map from omega to ml. Actually, maybe this is not the point that is most important to stress, but anyway, cross omega 2 ml to itself. Yeah, you have to normalize things correctly, but anyway. And you have a bundle over here, okay? And you can pull it back. So the pullback of nu is isomorphic to nu, direct sum nu. Okay. So this statement might seem a little bit strange, but actually if you familiar, again, I only have 20 minutes left, so you only have 20 minutes of listening to me. So if you're familiar with things in Floer theory, you know that like if you take two holomorphic disks and you put them together, then the kernel of the d-bar operator on the glued thing is basically the sum of the kernels on the two pieces. Okay? That's this multiplicativity. That's exactly this multiplicativity. Something, pullback, which is the pullback when you glue them together, that's one nu, is the sum of the two things on the two factors. If you really try to implement this, that's right. So to really get the formula like this, when you define this operator, you should assume vanishing at a point. At a point. Otherwise you get an extra copy of like the tangent space at that point. So that's exactly what. But this is kind of typical in the subject. Okay, so why am I doing this? I'm doing this because that means that we can take the Thom spectrum and this, well, we started with a space that had a product, and I explained last time you can think of it as an A infinity space, okay? And this is an A infinity ring spectrum. Or an A infinity, well, let me just say kind of, this is an associative ring spectrum. Okay. The reason this is associative is because this underlying space has a product, and the vector bundle that gives rise of it is multiplicative, even though there's no tensor product. Multiplicative just means that it's actually additive, but that's the terminology. Okay, and so now I can make the correct statement. So the correct statement is that Floer theory doesn't quite deform the stable homotopy type of this, it actually deforms the stable homotopy type of the Thom spectrum. So I'll state this now because now we're really at the part, it's like every lecture should end at the point where the speaker doesn't actually understand things anymore. So let's state this as a conjecture, because certainly this is not proved. Floer theory gives rise to a deformation, to an A infinity deformation of omega 2 minus. Okay, so in the last 15 minutes, there are some complements that I would like, some things that I would like to explain. So the first thing that I want to explain is that this bundle here is not mysterious. The stable bundle right now, it was introduced analytically, but in fact, we know essentially exactly what this nu is. Yes, twisting is this Thom spectrum. So twisting is the following thing. So if usually when we think about like a local system over a topological space, we could take homology with coefficients in that local system as some kind of twisted homology. Okay. In the world of stable homotopy theory, analog is taking the Thom spectrum of the bundle. It's exactly the same. In fact, you can, if your local system, is like a rank 1 local system, you can take the Thom space of that system, that local system, and compute its homotopy groups, and you exactly get twisted homology. So that's the analogy. First, okay. So the first remark is that the tangent space of M is classified by a map M to BU. Okay, so what does that mean? Well, M is a symplectic manifold, so M has an almost complex structure, which is canonical up to contractible choice. Up to contractible choice. Okay. And so then this is a classifying map for that tangent space, for the complex structure on the tangent space. If I restrict this map to L, then I know that then the fact that the tangent space of M restricted to L is isomorphic to the tangent space of L direct sum the dual. So this is some statement from symplectic geometry. If you have a Lagrangian inside a symplectic manifold, if you have a Lagrangian inside a symplectic vector space, then you can write down your symplectic vector space as that Lagrangian subspace direct sum its dual. Okay? And so this is just the analog for Lagrangian submanifolds. Split. This is kind of compatible with the symplectic form. What that means is that we have a lift. where this is the classifying space of real vector bundles. And this map takes a vector space to V, well, it's the same thing as taking a vector space and tensoring over C. Oops, tensoring with R over C. Okay? So now, if you apply the machinery of algebraic topology to this, basically you say, well, this will do some, so there is a homotopy fiber. So the fiber of this is exactly this kind of space of paths, what I've been calling the space of paths from PML. Just give me 1 second. Yes. So this induces a map from this to the fiber of BO to BU. Okay. And then you can continue looping more and more. The loop space of this is the loops maps to the loop space of the fiber of the map from BO to BU. And now this loop space is exactly omega 2 ML. Okay. I didn't explain that, but roughly speaking, if you start with, you take this disk here and you just analyze this disk as this family of paths. Oops, this was not a wrong disk because it has an x and a y, so let's just drop this. Let me draw that map. So this isomorphism here is just saying something like this. So I start with my base point, okay? And the base loop space of the path space should be based at the constant. Okay? So I take a family of paths from the constant, from the base point to L, okay, which go through L. And I can just sweep, when I do that, I just sweep out a disk. And then in the back until I come back to myself. So this is the isomorphism here. So this maps to the loop space of this fiber. And then what I didn't have, we didn't have time to discuss at any point, is that you can just apply Bott periodicity that this loop space of this fiber, omega 2 ML, maps to Z cross BO. And mapping to Z cross BO is exactly a stable vector bundle. Okay. And this stable vector bundle is exactly, by some theorem we have to prove something, is this nu that we were talking about, which is the index bundle we had earlier. And roughly speaking, what you have to prove is you have to go back to the proof about periodicity and understand what was happening in the index bundle. Now, just to make sure that I say something that some people can find familiar, there is a Z here. Okay? This Z is something that people know, it's just the Maslov index. And this Maslov index is what controls the dimension of the moduli space. And what I'm trying to say is that, we know how to make sure that the Maslov index is 0. We know how to trivialize this. If you want to make the Maslov index 0, then you go back and you say, well, I had some vector bundle on vector bundle on M, and I had some trivialization on L. So there's a characteristic class. In fact, there is a relative characteristic class. You make sure that relative characteristic class is 0. Okay, and then you get this output that this thing always lands in 0. But there are more things you could ask. There are higher characteristic classes. There are characteristic classes that are not in cohomology theory. There is actually this entire map. You could ask for this map to be trivial. Okay? So that's the first thing that I want to say. The second thing that I want to say is that actually this analysis is still we're still remembering too much. If you just want to know whether this theory here is twisted or not, that's maybe a question that, like, is this theory twisted or not? Do we have to put a twist? The question of whether nu 2ml is twisted is entirely determined not by this map from here to Z cross BO, but by further composite. Now I need to write something, which I certainly did not have time to. So it's something called B cross BF, where F is the monoid of self-homotopy equivalences of spheres. So this BF is actually very close to the sphere spectrum itself. It's basically the same except in dimension 0. Instead of getting a Z, you get a plus or minus 1. In particular, its homotopy groups are trivial in higher degrees. Rationally trivial. Whereas those of BO, they look like eight periodically. Okay? So there's plenty of Z's here and plenty of zeros here. Okay. So the point of making this remark is that when you try to use this, I didn't indicate anything. When you try to prove this, when you try to use the fact that the moduli spaces of holomorphic curves, they don't have trivial tangent bundle, but they're twisted, you don't need to trivialize the tangent space. So that's way stronger than what we need. Space of the moduli space of holomorphic disks. To get these maps, to get a Pontryagin-Thom map. All that you need is to trivialize the corresponding sphere bundles. You only need to trivialize the sphere bundles of the tangent space. So that means that to me gives a shocking implication, which is that we don't even need the moduli spaces to be to be manifolds. Don't need to assume that moduli spaces are smooth manifolds. In fact, we only need that they satisfy Poincaré duality. Whether this has any consequence I don't know. Of course, when you do Floer theory, if you work hard enough, you can, you usually prove that they are manifolds, and if you work really hard, you can prove that they are smooth manifolds. But the theory does not. Theory does not seem to use that. So the last things that I want to explain is that there is still much to be, that there are several issues that I didn't address. So one issue that I didn't address is what happens with boundaries. What about the compactification of the moduli space? I've basically been pretending that you just take the space of disks and you use the space of disks to do something with it. And the answer is that the answer takes two forms. So in general, the compactification has disk and sphere bubbles. So instead of just encountering a disk like this, you encounter a disk glued to another disk, glued to a sphere, glued to another sphere. Okay? And the disk bubbles, they don't cause any problem. They work exactly as in the Morse theory case, which I didn't explain, but what Cohn, Jones, and Siegel basically covered. Disks don't give any trouble. Spheres, however, they make the theory as I explained it completely break down. Or rather, multiply covered spheres break the theory as currently explained. And the reason is because we don't have, because you can't just, because then the moduli space, because they cause the moduli space to behave like an orbifold, and if you have an orbifold, then you need to figure out what Pontryagin-Thom theory means, because they make the moduli space into an orbifold. And that's exactly what that point over there was about. No integral Poincare duality. So you have to figure out, so again, that means that the theory becomes more complicated, but that's okay. And then the last thing that I want to explain, to mention, is that there is this conjecture here about somehow the deformation, the Floer theory gives rise to a deformation. What I did not explain is that there is, in Floer theory there is, there was just a lecture about A-infinity algebras. So did you mention curvature? No. Yes? Good. Last thing is curvature. Okay? So in this story, you have curvature. And so the curvature in this context Pardon?
You didn't call it curvature, you called it M0.
M0. The curvature, which equals M0, corresponds to the space of holomorphic disks, fundamental class, whatever, holomorphic disks, passing through the base point. And now, there is currently no framework for handling curvature in the world of spectra. Okay? And so this is what, this part is kind of joint work with work in progress, let's say. With Thomas Krog and Andrew Blumberg is to formulate this. Formulate this notion in the spectral case. Okay, thank you. Yes?
Among the two implications that you said, before the symplectic thing, you said that you can recover the stable homotopy of
omega 2 ML.
yeah, omega 2 ML. That's for any L embedded in there.
Yeah, any for any L, but somehow you all so earlier I basically had explained. Let me just erase this. So I have this. What did I call it today? Oh, yes. So today I talked about this kind of thing called S, X, ML. Okay. Well, clearly this thing makes there for any topological space. M is a topological space. L is a subspace. Okay. So I can't bear that. So I'm going to just call XA. Okay. So this is this is associated for all X in A. Okay. So there is actually a space S XA over A. Okay. There's another space over A called PXA, space of paths that start at the base point and end on A. Okay. There is a map from here to here. That's what we constructed. Now, what you want to do is basically you want to take maps. So it's really hard. I'm going to write something, but it's maps over A from this to this that are also over this. Okay? But you can actually formulate it directly, which is that, how can I do this? Oh yeah, but this diagram commutes. So if it's over this, then if it's over this one, then necessarily it's over this one. So you don't have to do it. You can just do this. Okay, so this is what we want. Now the problem, so I explained that this is equivalent to omega 2XA. Or anyway, this is equivalent to omega 2XA. The problem is that this thing is over this path space, which is infinite dimensional, which is too annoying. Okay, so instead what you can do is you can use the projection from this to this. In the more theoretic case, you use the projection from this to this. You take some kind of fiber of this over a fixed A, and you glue those together. That's the basic idea. Okay. Yes.
The fact that PF has relatively trivial homotopy groups, am I right to think of this that the main part of the twisting comes from the Maslov index?
Yes, although you have to be a little bit, yes, the main part of the twisting comes from the Maslov index. It kind of tells you that if you multiply things by sufficiently large numbers, then they become trivial. Actually, that's still, yeah, anyway, it becomes trivial. But actually what it tells you is something interesting. It tells you that the FP, so let's look at a manifold of dimension n, okay? Then there is some other number, let's call it m, so that if you pick a prime larger than that m, then the homotopy type is well defined. Then the homotopy type is untwisted. So there's a notion of like a p local homotopy type, maybe. So at any sufficiently large prime, where sufficiently large is some quantitative thing in terms of the dimension of n, you can make sense of the Floer homotopy type of Lagrangians inside symplectic manifolds, as long as you can deal with this sphere bubble issue and this curvature issue. Okay?
For example, if I only cared about exact disputes.
That's right, but if you only did exact M, there are no disks anyway.
No, the L.
No, because this map is non-trivial. Yes, there's no spheres, yes. The L need not be exact, so there's no spheres, this is not a problem. You can still have this. Yeah, so this is fine. This can handle. Absolutely right. Yes. That's right.